parallel operation of synchronous generators. Now, why do we operate generators in parallel? So, these reasons are similar to the parallel operation of most electrical machines in general, right? But still we will discuss this. One point is that several machines, if we keep together, then they can supply a bigger load, okay? Several machines can together supply a larger load as compared to a single machine. Okay. Now, another advantage is when we have so many machines in parallel. Let's say one of them is having a fault, then you can isolate it and the other machines will still supply the load. Okay. Having generators in parallel will avoid total power failure in case one of the generators fails to operate. Okay. Another similar reason, so this is what we call as reliability. Therefore, it will increase reliability of the power system in which it is connected. Okay. Similar reason is that if one of the machines need some kind of maintenance, okay, then it can be shut down while the other generators will still be operating. Okay. Having generators in parallel will allow one or more of these generators to be shut down for preventive maintenance. Okay. Now, another advantage is when it comes to smaller load as compared to a generator. Okay. Consider a generator which is having a rating of 100 MVA. Let us say this is the generator capacity or the generator rating, whereas the load that is required is only 50 MVA. This is the load capacity. Okay. So, instead of operating this generator which is having 100 MVA at a lower load, okay, this will cause inefficient operation. Okay. Instead of that, what we can do is we can take smaller machines, that means something which is 10 MVA, let us say. Then you can connect 10 of them in parallel. Okay, machine 1, 2, 3 and so on till 10. Now, when you have a smaller load, then only 50 MVA is required. Then you can operate only 5 machines. Okay, but if the load is increasing, 70 MVA let us say, then you can operate 7 machines. Okay, others can be shut down. So, in this manner, each machine is going to be efficient while the other machines are simply turned off. So, overall the operation will be more efficient. Okay. So, you can write this point as well. If only one generator is used and it is not operating at near full load, then it will be relatively inefficient. However, with several smaller machines in parallel, it is possible to operate only some of them so that those machines which are operating can run at near full load and thus more efficiently. So when two generators are connected in parallel, then what should be the conditions that should be followed? Okay, so this is also pretty straightforward. The line voltages should be equal. Why? Because if they are not equal, then there will be a circulating current, right? And similarly, the phase sequence should be same. Should be same. Once again, if the phase sequence is not same, then what will happen? There will be a difference in voltage that is created over a cycle, right? So phase sequence should also be same and the phase angles of phase A should be same. So you can take any phase, okay, phase B, phase C. The point is we have ascertained that the phase sequence is same, right? So that means if this is phase A, then this is phase B and phase C for machine 1, and for machine 2 also you have the same phase sequence, okay. If it is a different phase sequence, then what will happen? A might be here, B might be here and C might be here. So here there will be a difference in voltage that is created. Now what about the third point? Phase angle of phase A should be same. Now it can have the same phase sequence, but the phases, if they are not equal, like for example, let us say phase A is here and this is phase B and this is phase C. Now this and this have the same phase sequence, but phase A is a horizontal angle here, whereas this phase is going to have a different angle, so there will be a difference in voltage that is created, right? So that is why we have to ensure that the third point is also done. Now the last point is with respect to the frequency of the oncoming generator. So that means if a generator is already connected to a load and now you are trying to connect another generator onto the parallel operation condition. So then this generator is called as the oncoming generator. Okay. So frequency of the oncoming generator must be slightly higher than frequency of running generator. So why is this? This will ensure that the oncoming generator is not going to start working as a motor. Okay, so we will discuss why that is a little later. For now, you can just remember that frequency of the oncoming generator should be slightly higher so that it is ensured that it is working as a generator. Okay, to ensure it will work as a generator. So these are the conditions for parallel operation. Now how do you ensure that all of these conditions, how they are satisfied? So we will start with the first condition. So we can check the line voltages using a voltmeter, and if they are equal, well and good. If they are not equal, then we are going to adjust the field current so that the terminal voltage is equal to the required line voltage. Okay. So condition 1, how do you satisfy? Using voltmeter, the line voltages can be checked. If not equal, then the field of the oncoming generator is adjusted so that its line voltage is equal to that of the running system. Okay, so this is about the voltages. What is the next condition? It is the phase sequence. So how do we ensure that the phase sequence is the same? One method is to use a induction motor, a small induction motor. Okay, so if we have a generator here, this is already connected to a load. Okay, and the other generator, generator 2, we want to connect in parallel. Okay, so now what will you do is you will connect a motor here, a small motor, and you will check what is the direction of rotation. Okay, that is case 1. In the next instance, the same motor you are going to connect across generator 2, and then you are going to verify what is the direction. If the direction is same in both the cases, then it means that the phase sequence is same. If the direction is not same, then it means that the phase sequence is not same. Okay, as simple as that. So you can write down a small induction motor can be connected to each of the generators one after the other. The direction of, or you can write if the direction of rotation in both cases is same, then phase sequence is same. If the direction of rotation is opposite, in both the cases, then phase sequence is not same. And how can we change it? In this case, reverse two of the terminals of the oncoming or the incoming generator. Okay, so this will change the phase sequence. Another method, commonly used method, is the 3-lamp method. So this you can say this is method 1. Another method that you have is 3-lamp method. Okay, so in this case what is going to happen? You're going to make use of 3 lamps connected across each of the terminals of the generator. So that means if this is, once again we will draw the diagram here. This is the load generator 1 which is already in line. Now generator 2 has to be connected. Okay, so these are the 3 terminals. Now we have a switch here, another switch here, and finally for the third phase. Okay, so this is phase A, B and C, and here you can write A dash, B dash and C dash. Okay, now what will you do? You will connect a bulb across these switches while the switch is still open. Okay, so now what will happen? This bulb will either it will be switched on or off depending on the potential at A dash and A. Now if voltage is same, the instantaneous voltage, if it is same at this point and this point, then the bulb will not glow. But if it is having a non-zero value, then it will glow, right? Now since we have not yet decided that we've not yet set the phase to be same, let's say there is a small phase difference between A and A dash. Okay, now the same phase difference will be there between B and B dash, and between C and C dash also the phase difference will be the same if the phase sequence is same, right? That means if you take this as A, B and C, then let us say a slight phase difference with A dash, say this is B dash and this is going to be C dash, okay. You can see that this phase between each of the phases is going to remain same for whatever phase you're going to take. Now this difference is only what we need because the bulb is connected between A and A dash, okay. So if the phase sequence is same, then all of the light bulbs are going to get turned on and off at the same time, okay. So why they will get turned on and off, this you can understand by seeing the individual waveforms. If you consider phase A, then the voltage waveform, let us say it is like this, okay. So this is A. Now A dash is going to be having let's say a phase difference like this, right? This is A dash now. Now you can see that the difference between the two voltages, it is going on reducing, it is becoming 0 at one point and once again it is increasing, okay. Now the voltage in this case is the polarity is going to be reversed, but still it is a bulb only. Whether you draw current from this side or this side, it is going to still glow, okay. So the polarity is not going to matter here. Only thing that needs to be understood is that it will glow at one point and it will switch off at one point, okay, and once again the cycle will repeat. Now the same difference, since between each of the phases, like here I have told you, but since between each of the phases the phase difference is the same, all the bulbs will glow bright and they will switch off at the same time. Whereas if phase sequence is different, then what will happen? This is going to be A, B and C. Now A dash, if this is A dash, then this is going to be C dash and this is going to be B dash, okay. This is C. So now what is the phase difference between A and A dash? This is going to be here. The phase difference between B and B dash is this, C and C dash is this, okay. So since the phase difference is not the same anymore between all these three phases, the bulbs are not going to glow bright and dark at the same time if the phase sequence is different, okay. So you can write down, if phase sequence is same, then bulbs will turn on and off at all three bulbs. Then all three bulbs will turn on and off at the same time. If phase sequence is not same, then they will turn on and off in succession. So in this case, what you should do? In this case, two of the terminals need to be reversed once again. Same as we discussed for the small induction motor, okay. So these are the two methods that are available for setting the phase sequence. Now what about the next condition? We have the phase and the frequency. So both of them you can consider together. Condition 3 and 4. You can make use of the same 3 lamp method, okay. So first we can set frequencies to be very nearly equal with oncoming generator frequency to be slightly higher, okay. Why is that? So that the oncoming generator will work as a generator rather than starting to work as a motor. When it works as a motor, it will start taking power, Okay, so we can set the frequencies to be very nearly equal using a frequency meter. Okay, so we can measure frequency using a frequency meter and adjust the frequency of the oncoming generator. Next, you can take care of the phase. So you can make use of the same 3 lamp method. So how will that work? In the previous case, in the second case, we have just assumed that the frequency is same. So the phase difference between each of them is not varying. Okay, but if the frequency is not same, okay, we are keeping the oncoming generated frequency to be slightly higher. Okay, so when there is a frequency difference, what will happen to the phase? The phase difference between the generators is going to vary. So you can write down, since frequency is not exactly equal, the phase between each generator is going to vary. Okay, so when the light bulbs are dark, then phase between them is same, and this is when you will close the switch connecting both the generators. Okay, at this point, switch can be closed. Okay, so this is using the 3 lamp method. Using 3 lamp method. But this method is not very accurate. Okay, another method, better method, is to use a synchroscope. Using synchroscope. So what is a synchroscope? It measures the phase difference between the phases. It measures phase angle between the A phases of both the generators. Okay, so instead of a lamp, you are connecting a synchroscope. Now how will a synchroscope be? It is going to have a dial like this. At the center, if the dial is at the center, then it means the phase difference is 0. Now if the frequency is of the oncoming generator is higher, then this dial is going to move in the clockwise direction. Okay, so this is what you can say fast. If the oncoming generator is slower, that means the frequency of the oncoming generator is slower, then the dial will move in this side, anti-clockwise. So this is slow. So what is the desirable condition? The dial should be moving in the clockwise direction. So that is when it shows that the oncoming generator is slightly faster. Okay, and at that point we can close the switch. So you can write down, if frequency of oncoming generator is more than running system, then phase angle advances and the synchroscope needle rotates in clockwise direction. If frequency of oncoming generator is less, then needle will rotate in counterclockwise direction. Okay, so this is how you make use of synchroscope. Okay, so this is how you ensure that all of the conditions for paralleling the generator are satisfied. But in practicality, all of these are old methods. Okay, currently this is all automatic. The paralleling of generators is all automatic.